Hi folks! Today I welcome you to a Pecha-kucha style journey into the mysterious world of particle physics. My name is Lakmin Wickremasinghe and I will be narrating this presentation together with our one and only Higgs-chan. So let's get started. Let me first take you on a journey to the subatomic. As you all know, a drop of water constitutes of so many water molecules. And water molecules, as you all know, are made up of two hydrogen atoms and one oxygen atom. But what are oxygen atoms and hydrogen atoms made of? They're made from a bunch of protons and neutrons orbited by particles called electrons. But we now know that protons and neutrons can be split even further into smaller particles called quarks. The electrons, however, cannot be split further. These are known as fundamental particles. Now, there are six types of quarks in the quark family. For electrons, they have two other similar particles, and these three have their own respective neutrinos. These six build up the lepton family, and this set of 12 particles are the ones which make up all the known matter in the universe. However, there are also four types of particles which are responsible for the four fundamental forces in nature. The photon mediates the electric and magnetic forces. The weak bosons and gluons are responsible for the weak and strong force. Finally, the graviton is said to govern gravity. This set of matter particles and the force carriers, together with our one and only Higgs-chan, makes up what physicists call the Standard Model. And today, we know that this is the best theory which explains every phenomenon in the universe. So let me take you through a real-life example of this next. This is one that you all are experiencing at this very moment. How a picture or a video is taken through a camera. Here, photons scattered from you interact with pixels in the camera sensor, which generate electrons. This is what's used to build the picture of you shown on this very screen. Next, it's time for a world tour of some physics experiments. Our first stop will be CERN in Switzerland, and then we'll head to Kamioka in Japan. Our third stop is somewhere you would least expect. Yes, Antarctica. And our last stop is not even on Earth, it's on the International Space Station. CERN houses the biggest machine in the world. The 27-kilometer Large Hadron Collider, or LHC for short, is housed 100 meters below the France and Switzerland border and was responsible for discovering, yes, you know who, the Higgs particle. And this led to the Physics Nobel Prize in 2013. The Super Kamiokande in Japan is another massive detector filled with 50,000 tons of water. This amazing detector was responsible for proving that the three types of neutrinos can actually change between themselves. How cool is that? This mind-blowing discovery back in the 90s earned them the Physics Nobel Prize in 2015. The next stop is the Ice Cube experiment in Antarctica. This colossal detector traverses 3 kilometers deep into the polar ice. Check how small the Eiffel Tower is next to it. This detector looks at particles which shower down on Earth due to cosmic rays, which is also the phenomenon that generates aurora. So, from the story so far, it looks like we have figured out or figuring out everything. But that's not true. For example, from all the energy in the universe, we only know 5% of it. The rest is said to be made from dark energy and also dark matter, which is where our last stop, the AMS experiment located on the International Space Station, comes into play. One of its main goals is to look for dark matter particles. One such example is of the Higgs particle, which scientists predict might be a possible candidate for interacting with the dark world. But how is the situation with other physics phenomena? So eventually, we wish to reach energy scales of the Big Bang to unravel its mysteries. But for that, we still have a long way to go, because even the most powerful accelerator on Earth, the LHC, can only reach less than a billionth of that energy. Hence, all experiments need to be improved. The Super Kamiokande plans to upgrade to Hyper Kamiokande at an estimated cost of 32 million US dollars. The ice cube will be upgraded to the second generation ice cube detector at an estimated cost of 350 million US dollars. And the LHC? Well, CERN plans to upgrade it to a colossal 100-kilometer future circular collider. The cost? More than a whopping 20 billion US dollars. But even after construction, there are obvious concerns of operating them. For example, even the current LHC has an operating cost of roughly 1 billion US dollars per year. This has been a major concern for scientists for decades, which is why they have dedicated a lot into developing greener and sustainable solutions. And finally, we see these ideas slowly bearing fruit, like the one here developed in the US. This can also miniaturize the whole machine, immensely reducing construction costs. And with the miniaturization of accelerators, we also have the possibility of miniaturizing detectors, like the one shown here in CERN. Instead of brute force techniques like smashing particles together, they look at going for more precision. It's actually similar to how particle physics was done decades ago. For sustainable power, switching to solutions like nuclear fusion can be the best option. Nuclear fusion, which is different from traditional nuclear fission, is equivalent to harnessing the power of the sun. And this is finally becoming a reality thanks to various research groups around the world. And even though there's still much to be done till we get there, these sustainable and greener goals will definitely push the field forward and also push us to innovate amazing technology that will benefit everyone in the world. Thank you all for joining me in this journey.